Welcome to the SEI podcast series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Hi, everyone. Welcome to the SEI podcast series. My name is John O. Spring, and I'm a senior vulnerability researcher here at the Software Engineering Institute's CERT division. Today, I'm pleased to welcome Alan Householder and Nathan VanHoudnos in discussing the management of vulnerabilities in machine learning and artificial intelligence systems. Welcome to you both.
Thanks, John.
So let's start off and talk a little bit about, the work that we each do here a bit. Alan, do you want to start and talk about what your work is?
Sure. So I too am a vulnerability analyst within the CERT Coordination Center at the Software Engineering Institute. Been doing this for a number of years. Started off in incident analysis and have done some malware analysis stuff along the way. A lot of the common thread that runs through my stuff tends to be more modeling and math and simulation things surrounding vulnerability management, vulnerability analysis, done some work in fuzzing systems, done some work with coordinated vulnerability disclosure, but generally applying different ways of modeling the processes and things that can go wrong on the software vulnerability side of the world.
Great, thanks. Nathan, how about you?
So I'm a senior machine learning research scientist here at the SEI. I'm essentially running the adversarial machine learning portfolio. Adversarial machine learning is this idea that we have machine learning systems that do different things for us, and we also want to often run them in situations that have adversaries. So, for example, an adversary might make your machine learning system do the wrong thing. It might make it learn the wrong thing. It might make it reveal the wrong thing about your training data. And so much of my work here is about understanding how we do machine learning well and understanding how we can make it secure and robust.
Great, thanks. So, over the last 3 years, we've seen a lot of examples where real-world machine learning systems have been tricked in one of the three ways that you mentioned, Nathan. So like Google, Amazon, Microsoft, Tesla, all have seen examples of this. What's the current threat landscape look like for machine learning systems, and how does that intersect with our work in vulnerability coordination?
So generally what happens is that you have a bunch of academic researchers that try and take these different machine learning models or machine learning systems and play with them. You mentioned the Tesla attack, right? That was a lab out of Tencent looking at what a self-driving car would do and figuring out how they could, in fact, cause it to change lanes by only modifying a little bit of the road, specifically putting some small stickers to change to make it think that it needed to change lanes when it didn't, right? In terms of the thinking about the normal threat landscape that we would sort of think about in the cyber domain, what we mainly see is proof of concept stuff in the machine learning systems. We haven't really seen a lot of very specific, robust attacks to machine learning systems at this point, but that doesn't mean that they are not coming down.
And I think on the traditional vulnerability coordination side of things, what we've seen is we've had two vulnerability notes that CERT has put out in the past couple of years about machine learning related vulnerabilities, and they actually are examples of two very different sort of abstractions of vulnerability. One being a vulnerability in an antivirus system where it was trivially able to bypass the trained model because you just appended a little bit of text to the end of a file, and it could be, the executable could still get through, but the detection would fail. And that was an example of, a specific instance, specific product, kind of a traditional vulnerability. It was just sort of a novel method for how that vulnerability was exploited. The second one that we put out was about any system using gradient descent being vulnerable to a particular kind of attack. And essentially it comes down to, and that's some of the impetus for the examples in this paper are this idea that the problem might actually lie in just the way the system was built, and it's not necessarily that it's a code bug. It's not a thing that you can go patch easily. It's just if you use this technology, you will have vulnerabilities or have problems that could be vulnerabilities like this.
So Nathan, you mentioned that the attacks aren't robust yet. Does that mean that they're hard to find? Oh, just are there relatively few known attacks, or is it pretty easy to find an attack on a machine learning system?
So it depends on how much access your attacker has to the system. So, for example, if your attacker has a copy of your trained model file, right, like actually can load the neural network, for example, that you're using in memory, then they can design something that will fool it very simply. If your attacker doesn't have access to your model, their job becomes harder. Another way that, other than sort of adversary knowledge, another issue is what kind of control they have over the input to that model. If they can actually modify, say, the images that are coming in and directly modify specific pixel values, then they can totally just arbitrarily control what the system does because they can control its inputs exactly. If they instead have to do something like put physical objects on the ground, as in the case of the Tesla example, that's a lot harder, and making those attacks robust is much more difficult. And what I mean specifically by robust there is that we've got a self-driving car designed by Tesla, so we have an attack against Tesla. What about a different self-driving car made by a different company? That attack against Tesla may not work against that other self-driving car. That's what I meant by robust in the attacks.
Interesting. Okay, thanks. So we talked a little bit about this stuff in a paper at the New Security Paradigms workshop last October. Alan mentioned the paper. The thought experiment that we walked through there was, so there's a problem with a Tesla, the machine learning system. Does something like that get what the vulnerability management community understands as a vulnerability identifier, a common vulnerability enumeration ID, CVE ID, right? So I know we used a different example in the paper, but everyone could go read that if they want.
Please do, in fact.
Yeah. But for the flaw in the Tesla where you can make it change lanes, or the drone can project a stop sign on a tree and cause the Tesla to stop, Alan, do you think that those are things that should be given CVE IDs to facilitate communication to, say, the owners of Teslas?
So a lot of that gets tied up in whether or not it gets a CVE ID might be distinct from whether or not it should be a vulnerability and treated like a vulnerability. So to be clear here, CVE IDs are an identifier that are assigned. MITRE Corporation actually operates the CVE list, and it's intended to be a dictionary of identifiers, and then the definition, which is basically a description of the product and the vulnerability, and something that uniquely identifies it from other vulnerabilities potentially in the same product, even if they're potentially similar vulnerabilities. But not all vulnerabilities get CVE IDs. So, for example, a website vulnerability in a website, may not get a CVE ID because there's really only one instance of that website, and once it's fixed, and there's nothing for the users to do. So, if it requires the users to take some action to patch, then having IDs so that you can coordinate those actions can be useful. If there's nothing for the user to do, if it's just going to patch automatically, and I'm not familiar enough with Tesla in particular to know, do they have an auto deployment system that they can just push patches out? If they can, and if it's totally under the control of the vendor, the supplier of the patch, maybe it doesn't need the ID. And in the paper, we go into a lot of gory details of, MITRE has put out a list of criteria for how to know if you should assign a CVE ID, how many IDs should you assign given the description of the bug and everything. I don't want to belabor that because it was it was pedantic enough going through it the first time to write the paper, it will bore most of the folks listening to me right now. So, but the end result there is, given those rules, you may or may not come out to that answer of assign an ID or not, and that doesn't necessarily mean that it shouldn't be a vulnerability. You shouldn't treat it like that. Treat it, the way we treat other software vulnerabilities.
Yeah. So, Nathan, with this sort of a situation, who currently talks about these sort of problems? Like, what's the community that's currently talking about them, and how does it intersect with the community of people that use sort of CVE-IDs to talk about problems?
Well, so that's a really interesting question, right? Is that adversarial machine learning as a field is this academic discipline that essentially sort of started because people wanted to play around with these machine learning models back before people were really using machine learning in practice, right? And so the AML folks are a pretty different set of people from the security folks. And mainly what happens in the AML community is that people publish papers, they drop them on archive, and maybe they'll put something on GitHub that shows, hey, this is a particular attack, or this is a particular defense. And there's this really quick iteration between attacks and defenses where once a defense gets put out, attacks very quickly break it. That kind of thing that's happening in the community. But there's essentially no discussion of coordinating these kinds of problems that are showing up in systems that people are actually using, except for a couple of different points. For example, one of the things that we reference in the paper, when they released GPT-2, they released it in stages so that they wouldn't be dropping this possibly dangerous machine learning model out there for people to play with and get hurt by. And then there's also some other efforts. Jono, I know that you're working with some folks who are doing an AI incident database, seeing how they can sort of help let people know about these kinds of things before people put these into products. But my understanding of those efforts is that those are more focused on, these are the ways that these things can fail in general, not these are the specific ways that these things have failed. Let's fix these specific things in these specific products.
Well, that's right. And it mirrors sort of the challenges between safety and security in general, right? So there's a lot of, say, safety-focused people in the automobile industry.
Mm-hmm.
There are a lot of security-focused people for the computers that operate in vehicles. Even those two groups of people don't talk terribly much, because the heuristics that you need to use to find a security flaw are rather different than what you need to do to find a safety flaw.
Even if a security flaw reveals a safety flaw.
Yeah, so I think that Bruce Schneier talks about the difference between making sure the Tacoma Narrows Bridge doesn't oscillate and fall down in the wind, the famous, right? So basically, like, protecting the bridge against sort of random variation from nature versus protecting the bridge from a group of people who are trying to bore into it and plant charges to bring it down.
Yeah, those are pretty different.
You would do rather different things in your engineering of the bridge. So if machine learning engineering also needs different approaches for safety and security that are different enough that they are sort of different approaches. Alan, do you think that using some sort of common parlance to connect to the security community would help the adversarial machine learning folks to do that?
I think so, especially when we're talking about what the effects of a machine learning weakness might be. So, there are plenty of situations where you may have a machine learning system. It has a problem either, in the data that it was fed to train it, or in the inputs, or people could mess with it, but maybe the impact of that is almost nothing. In cases where it actually does have potential safety impacts, self-driving vehicles or even semi-autonomous vehicles are a really important safety impact. So therefore, if the AI is able to cause a safety problem, then you do have a need to be able to communicate that with both the safety folks and with the security folks. And a lot of this has to do with traditional security vulnerability analysis would look at things like what's the attack surface of the software, what are the untrusted inputs that an attacker could potentially give it? And Nathan mentioned you could have stickers. Amazon sells a T-shirt that's just all stop signs. If I wear that and I can cause cars to stop on the road, have I exploited the vulnerability? Well, maybe. So there's a communication need there. And in the paper, we talk about this idea that came out of MITRE, which is actually part of the background for why CVE is a thing. With CVE, you have traditionally you have security analysts and you have software developers. Those communities used to not talk to each other. Now you have things like DevSecOps, where it's everybody's on the same team and we're all trying to do the same thing. But back in the old days, that wasn't the case. So you needed a way to be able to say, you have this problem and we have a common identifier between them, and that becomes, and they go into talking about boundary objects and trading zones, and this goes all the way back to some sociology around, back in the old days when you were at a shipping port and you had lots of people who showed up with different cargoes and they all speak different languages, but you need to be able to exchange goods for money and so forth. And so you wind up with these boundary objects, which money is a boundary object where I exchange. We agree on what money is. We don't have to agree on whether or not the bread is worth the same thing to each of us, but we agree on money. So money becomes a boundary object. But even things like identifiers on cars and VINs and ISBN numbers and all of those IDs become trading things, because an ISBN is useful for a publisher to keep track of what things they've published. It's also useful for a bookstore to do inventory on which books are on the shelves and how many of each unit they have. So for vulnerability management, where you're trying to track, what bugs do I know about that are potentially security affecting? How do I know if I fixed them all, if I fixed everything that I know about? IDs assigned to that, especially common ones where we can, if you're talking about this problem that you know of, and I'm talking about this other problem that I know of, can we differentiate? Are we talking about the same thing or not? That's where identifiers really come into use here. CVE is not the only identifier that's useful here in this space either. There's also CWEs, common weakness enumeration, which is more for like the classes of problems you might have. And we go into that in the paper as well, where we kind of look at most of it is talking about CVE IDs, but CWEs may also be an appropriate way of identifying categories of problems. And I think since we put the paper out, CWE has even been updated a bit to start to address some of those categorization problems of ML.
I don't remember if I have it memorized, but it might be CWE 1035 or 1039. I don't remember. Anyway, there's one for machine learning stuff.
Oh, cool. I didn't know that.
Yeah, it basically is very similarly defined to the all things trained by gradient descent have a problem, but a little bit more general, which is interesting for our sort of CVE, CWE discussion, if they have their CWE as something slightly more general than this one algorithm has a problem.
So what's weird about this one algorithm having a problem is that in traditional software, there's a bug, and there's often a line of code that we can fix to fix the bug, right? But in machine learning, we don't have a line of code because we write code to train these models, right? We don't have a line of code to change that fixes this problem, right? We don't know how to do it yet.
So Nathan, is that our knowledge problem, or is that because you presume that there's a bunch of interdependencies and they have to all be changed, or it doesn't work?
To reflect the question back to you, are you asking whether or not, if we knew more about machine learning, like our machine learning science took off, we would know what to change, or are you asking something else?
That's my question.
So I'm going to give an opinion here, right? Generally, when I think of machine learning systems, I think of systems that are not specified. Like in a traditional software, you go through requirements gathering, you specify it, you write it down, you implement it, and if there's a bug, one class of bug could be that your implementation was wrong from your spec, right? That'd be one kind of thing. In machine learning systems, they don't operate that way. What we do is we give them data, and then we train them from those examples in that data. And so even if the machine learning works perfectly in the sense that it exactly captured the patterns that we gave it in the data, it's not necessarily true that that we constructed a data set that would teach the machine learning algorithm what we actually wanted it to be taught. And
Sure.
so there's sort of this issue where training things and then checking what they know is just super hard.
Sure. But I don't we get a little bit lost in the metaphors here? Like I don't train a machine learning algorithm like I train my dog. I write a piece of code that exemplifies the training methodology, and I can write some other code that exemplifies the data gathering methodology or expresses it, sorry. And so if the flaw were, use this algorithm instead of this algorithm, I can change the import statement in my uh, Jupyter notebook or whatever.
So one of the things that we talked about at the very beginning is there are these different classes of attacks, right? We can make a machine learning system do the wrong thing. We can make it reveal the wrong thing. We can make it learn the wrong thing. Let's dial in on learning the wrong thing for a second. Let's assume that we have a perfect machine learning system that doesn't have any problem. But what an attacker can do is they can modify the data in a particular way, such that now when that perfect machine learning algorithm comes and learns, it learns what the attacker wanted it to learn, not what the person who is designing the system wants it to learn. So does that help answer your question? Because that wouldn't be fixed with, for example, a new import statement. The import statement here is fine.
But it would be changed by, say, changing the lines in the data that were injected by the attacker,
The instances of the data, sure.
which is still code to change, right?
Well, it depends on how you're collecting the data, but sure.
I mean, it's all code at some point, right?
Uh, I guess images come off of a sensor, that kind of thing. Sure, it's all code at some point.
Well, yeah, I guess there's interesting questions about the physical attack objects, right? So, Alan, would you say give the pair of glasses that might make me like appear to a facial recognition algorithm as Tom Hanks rather than myself? Would you
You're
say
not
that
Tom
those?
Hanks.
I know that I'm very dashing, but I am not, in
Yes.
fact, Tom Hanks. Um, so, do those glasses deserve some sort of identifier? Like, are those an attack? Are we going to have to start giving CVIDs to physical objects?
So in the case of Tom Hanks glasses, or glasses that make everyone look like Tom Hanks, I think the the actual question there is, what is the security impact of that use? So if it's just simply that the Instagram filter that tags Tom Hanks in photos goes nuts, that's probably a problem for Instagram. It's probably not a security problem. It's a data integrity problem for them, which they may treat as a security problem. But I certainly wouldn't think that I had been hacked if I had posted a photo of myself wearing these glasses and it suggests Tom Hanks as a label. However, if I was using facial recognition for identification and entry into a physical facility, and Tom Hanks was authorized to be in there, I am not, and I show up wearing my Tom Hanks glasses, and the camera takes my picture, and the door unlocks and welcomes me in. Yes, there absolutely is a security flaw in that system, but I think that would be localized to the system in which that flaw was deployed, and not necessarily to the fact that that flaw is possible.
Mm-hmm. Great. Thanks for those examples. Um, Nathan, can you connect this a little bit to the other sort of work you do around AIML and how that contributes to sort of AI and ML engineering and what your sort of broader goals for engaging with vulnerability coordination are?
Sure. So one of the things that's sort of currently happening in the field is that generally machine learning and AI more broadly is not so much an engineering discipline as it is a bunch of heroic efforts. Someone will put together a really good team. That really good team will do some really good work. And you can list off where those teams are at major companies and at major research universities and those kinds of things, right? Um, but there's not like this set of rules and practices where we can say, okay, if you want good AI systems, do these several things, right? Well, the SEI has put out a list of foundational practices for AI engineering. We have an AI engineering effort that we're trying to kick off through ODNI, right? But we're still very early stages about how we make AI systems repeatedly and well. Um, my major interest is about robustness of machine learning systems and their security. So, and I put those in that order for a particular reason. Right now, if your ML system doesn't work very well, then it doesn't matter if an attacker is going to attack it because no one's going to deploy it anyway, right? You have to go back to the Tacoma Narrows Bridge example, you have to have a bridge that won't fall down just because the wind is blowing before you start worrying about protecting it from the people who are, trying to blow it up or whatever, right? And so the vulnerability coordination work is perhaps early because in a lot of these domains, people just aren't using ML for mission critical stuff yet. But if we look at how things have been going in the last 10 years, we fully anticipate that both industry and the DoD will be using machine learning systems in mission critical things. And we want to make sure that we have the infrastructure ready to respond to these kinds of failure modes.
Thanks. Alan, can you tell us a little bit about sort of the vulnerability coordination work with CISA and sort of how CertCC's role has evolved over the last, is it 32, 33 years now of sort of vulnerability coordination and the way that we've transitioned this sort of stuff to emerging technology groups?
Sure. In 3 short sentences, I can summarize 33 years of work.
I'm sure that you can provide some links in the show notes for some of the more detailed things.
Yeah. So the CERT Coordination Center, started in 1988 after the Morris worm, which was caused by somebody who wrote some code that exploited some vulnerabilities, and very shortly thereafter, more vulnerabilities, I believe, an FTP server were discovered, and that was one of the first things that CERT put out as an advisory back in the 80s. We can jump ahead 20 some years and say that continued to happen, and during that time frame, during that 20 years or so, up until the early 2000s, even large vendors really still weren't taking vulnerabilities very seriously. They would kind of treat them as annoyances, but they weren't necessarily really getting into patching and issuing updates and things just because of security vulnerabilities. That all started to change in the early 2000s. Folks cite the Bill Gates security memo as being a real turning point for Microsoft, and a lot of the industry kind of followed suit after that. As around that time, DHS was created, and there was a recognition of, so CertCC had been originally chartered by the Department of Defense to do this service for the whole internet. If there's a security problem on the internet, call CertCC. There's a hotline you could actually, there's a phone number you could call and get help. The internet got a little bit too big for that. Probably before we noticed that it got too big for that, and so the roles shifted towards, rather than responding to incidents, it's more about figuring out how to teach a community of folks to respond to incidents and respond to vulnerabilities, and building that community. That's the form of incident response team first, form of incident
response and security
incident
teams.
response and security teams.
First.org, everyone. Go check it out.
They've been around almost as long as CertCC has, because it was a recognition even then that this wasn't the thing that you could have a handful of people in Pittsburgh taking care of for the whole planet. So our role has developed over time in conjunction with Homeland Security and the development of what initially was U.S. CERT and now has become CISA as a separate agency within DHS. And CISA's role is really to protect the critical infrastructure of the United States. And the internet plays a role across all of the critical infrastructure sectors. Go figure, people have computers to do their jobs, no matter which sector you're in. All of those computers have software on them. Most software has vulnerabilities. So there's a distinct connection there between your ability to fix software vulnerabilities affects critical infrastructure. So CISA's interest is in that. They also have the responsibility for the civilian side of the federal government.
So we saw like sort of a first wave of people having a hard time recognizing that vulnerabilities were a thing in the 90s for the general IT vendors, right? And then I think what you're saying is that we saw a second wave of that that's still going on with the operational technology people in the critical infrastructure sectors, sort of following a similar growth pattern.
Right. So all of the places where you used to have manufacturers who produced durable goods, and they added a little Wi-Fi chip to it, or they added a computer and system on a chip, so you could have an app that goes with it. Those become part of that attack surface for critical infrastructure, as well as all of the operational technologies.
And this is like the sort of smart
systems.
light bulbs getting recruited to botnets because they're running some
Right.
ancient version of Linux because the people who make the light bulbs never set a way to update the operating system.
Right. And so suddenly every company in the world is now a software vendor, as well as being whatever products they produce. Yeah. So they have to think about how they're going to deal with those vulnerabilities.
Do you see a similar pattern evolving in the way the machine learning community is growing and adapting to its own importance and distribution in the world?
I think ML is going to show up in a lot of places. Hopefully it doesn't come as a surprise to ML practitioners that they're using software and that they might have software vulnerabilities to deal with. But I think there is, as Nathan already mentioned, there is a difference in communities here where the communities aren't necessarily used to speaking to each other on those terms. And
Nathan, would you call the machine learning practitioners software engineers or statisticians?
Are you trying to get me in trouble?
Yep. My point being, right, so Alan made the assertion that the machine learning developers are software engineers, so clearly they know there's vulnerabilities in their software and how to manage it.
So you nerd sniped me, so you have to content yourself with my response. Machine learning and statistics are two different fields that have their own sort of lore and their own sort of way of talking and their own sort of way of doing things, right? I am myself a statistician. My PhD is in statistics from Carnegie Mellon. So I'm sort of from this side, but when I introduce myself as a machine learning research scientist, right? And so modern statistics and modern machine learning basically do the same stuff, but we think about it very differently. And so the machine learning people who do machine learning research don't think of themselves as software developers. They often think of themselves as computer scientists in the sense that a computer scientist is different from someone who writes software. Right? Similarly for statisticians, often think of themselves as applied folks who will write the code that they need to write to get a job done. But neither of those communities really think of themselves as like developers. That's why we have fields like other titles like data scientist on the statistician side or ML engineer on the ML side.
I think there's an operationalization that's going to occur across ML because right now there's a lot of theoretical work, and there is some actual operational work that's starting to happen where companies are deploying ML models into production systems today, and the applications of that will only continue to increase. So I think as it gets operationalized, it's going to have to go through the similar transformation to what IT operations has done, where we went from in the 90s and earlier, it was possible for individuals to log into individual machines and type commands and upgrade software and things. And now you have, scripted and orchestration, and you have all sorts of tools to help you do that. And lots of engineering thinking has gone into how do you build robust systems out of non-robust components in traditional IT. And a lot of that came from the fact that having fingers on keyboards doesn't scale to thousands of computers within an organization, or hundreds of data centers. I mean, that's the scale at which computing and ML stuff is going to be deployed. So it's going to have to start off with that engineering approach of, not only how do we, and some of it also is because ML models will change as the data changes and as they get retrained and everything. So they're already going to have to think about this idea of, if there's a problem with my model and it's costing me money, I need to be able to fix it and redeploy a new thing very quickly. Well, that's the same pipeline you want to have for security problems anyway. So like the mechanical parts are going to show up just because of the fact that ML in its importance will become critical, and therefore having it be maintainable will become critical.
That's not to say that there aren't like ML product owners and ML engineers and ML research scientists that all do these different tasks. Like, didn't mean to imply that.
Yeah. So, we have this thought experiment or two, really, of, well, what if we apply CVE-IDs to these different parts of the ML pipeline? What would each of you like a reader or one of our audience members to take away from that work? What's the thing that people should know and take away and change what they're doing?
Major takeaway that I would offer to people is that if you're using machine learning, you're using it to solve a task. And the reason that you're using it to solve a task is because you want something done. If the doing or not properly doing of that task has an implication for your security posture, then you need to think about what the failure modes of the machine learning system imply for security. An ML system is not secure. It's secure for what purpose? You have to think about your security policies, and then you have to think about making sure that those security policies are met when you introduce this new shiny ML thing into it. That's the main takeaway that I would want someone to have from the paper.
Great, thanks. Alan?
I'm just going to echo what Nathan said. I think understanding your threat model, understanding what you need the system to do, what its attack surface is, and having a good understanding of what the implications are if someone messes with that is really the most important piece here. We've talked about how there are lots of applications where ML may be deployed and it doesn't have any security implications at all. You may have quality problems, but it's not security related. And one last thing, because these things are getting deployed in so many places where safety is an issue, the SCI has done some work on the intersection of security and safety as well. And I really, personally, my personal opinion is that you can't be safe unless you're also secure, because if the security gets messed with, then your safety claims sort of go out the window. So security, safety, and robustness are really very tightly coupled, and the systems need to be engineered to be all three.
Thanks. So I know that we've produced a guide for machine learning and cybersecurity. We have this other work on vulnerability categorization and prioritizing vulnerabilities with SSVC. Nathan, you mentioned your other work with robustness and security stuff for AML and the AI engineering and the various other things. What's next for our work in this area in the intersection between ML and vulnerabilities, do you think?
I think getting people to join us is a lot of what's next. For example, Microsoft and MITRE are certainly thinking about these things. The folks that you've been talking with, Jono, about the AI incident database are thinking about this stuff. There's a lot of community building, I think, that needs to happen so that we can sort of achieve some critical mass and actually get some things done. It's not that we don't know what to do, it's just that we haven't done it yet.
Alan, what do you think?
I think there's a good bit of bridging to be done still, where you've got communities who are using different vocabularies to talk about similar things. And in some cases, they're using the same vocabulary to talk about different things. And that's actually probably the more insidious problem to be aware of, is the unrecognized mismatch between you use a word and I use the word, and we both think we're talking about the thing that we think we're talking about, but it turns out that your idea and my idea are different. So building some of those common vocabularies, common concepts, and getting people on both sides, the ML and security side, to understand those things. Again, coming back to this idea of creating trading zones, and I think that's really where community building will help do that, because it brings more people into the room to start to develop those vocabularies and that understanding.
Yeah, and just one, Nathan, you mentioned this, but Ram's work with Microsoft and that community building there, we'll put a link to that stuff in the show notes as well. Alan, Nathan, thank you so much for joining us today and talking to us about a very nuanced topic, I think. for all of our listeners, there's be links to all of the resources that we've talked about today in the show notes for anyone who wants to dive in a little bit more detail. Alan, Nathan, thank you very much.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, Stitcher, TuneIn Radio, Google Podcasts, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.